So yeah, thanks again for the opportunity to talk here. This is joint work with Guo Chuan Thiang. So this is part of a joint project where we study mathematics related to topological insulators and topological phases using methods from coarse geometry and operator algebras. And let me very basic start with the description of a quantum system that will be relevant for the talk. So let's say we have a Hilbert space of states, and the dynamics are just, the very basic level described by some Hamiltonian, which is just some self-adjoint operator acting on the Hilbert space. And typically what you have is some spatial structure on that Hilbert space as well, right? So your Hilbert space is built together from local pieces where you know which part of the Hilbert space corresponds to which part of the space. And basically, there are two ways how this happens usually. So either, which would be labeled the non-interacting case, where you would say, well, if I have two disjoint parts of space-time, then the Hilbert space corresponding to the union is just the direct sum of the individual parts. And then there's the interacting way where you say it's the tensor product instead. And then, very sketchy, there should be some kind of second quantization map, functor, whatever, that sends non-directing systems to an interacting system, or the multiparticle description. So last week I think we were mostly, like in the lecture series, we're mostly in the interacting part of this, and this is also where the Kitaev conjectures are mainly about. And so the story that I'm going to tell you is about the interacting world, non-interacting world. And so basically what happens there is that invariance can be captured with K-theory of algebras. And so here's how this works. So gapped Hamiltonians are basically the basic ingredients. So we have a Hamiltonian, and we assume that it's gapped. And so that means that so a certain number, a certain value is not in the spectrum of a Hamiltonian, which is usually called the Fermi energy. And so the general assumption is that there's some observable algebra that the Hamiltonian is associated to, meaning that suitable functions of the Hamiltonians are, sorry, this is a typo, so this should be a continuous, convexly supported continuous function on R, right? So that I can take the function of this Hamiltonian using functional calculus, and then I want this to be in the operator algebra that we carried out. So that's sort of a choice of observable algebra that we have to put in. And depends on what we want to do ultimately. And so what can you do with this? So if you can take functions, so because you have the spectral gap, basically you can make the indicator function of that spectral subinterval continuous. And so that means that the projection onto the spectral part below the spectral gap is going to be an element of your algebra. And it's a projection. And so that gives a class an operator K-theory. So the group K0 of A for an algebra is defined by projections in that algebra. Or more formally, you can also allow projections and unionizations and matrix algebras over that. But at the very basic level, if you have a projection in A, that defines the K-theory class of that algebra. Okay, so now the question is, how do we detect non-trivial K-theory classes? So the idea is basically, we have this physical system which is gapped, and now we get this K-theory class, and we're interested in, is this a trivial phase or a non-trivial phase? And how do we detect this if we're given, just the Hamiltonian on an actual system, right? And what you would do, I guess, what in physics is you assume that the Hamiltonian is translation invariant, like it acts on a lattice, say ZD, and you assume it to be translation invariant. And then also the spectral projection will be translation invariant. And then you can take the Fourier transform, and so this projection will just be like a matrix valued function on the torus, right? So you use that translation invariant operators are the same thing as like under Fourier transform correspond to multiplication operators. until you multiply with the matrix valued functions if you allow local degrees of freedom as well. And then physicists usually draw pictures like these where they plot the eigenvalues of this matrix over certain paths in this torus. And what you can then construct are the Berry curvatures, which are these particular integrals over certain subtori, two-dimensional subtori. And these are really just, it's really just the first Chern class mathematically of a certain vector bundle you can construct on the torus. But so what happens if the Hamiltonian is not translation invariant? That's a very basic question. And I think, well, I mean, at least in the theoretical physics community, it's quite open to some extent what you do then. And one answer was given by Kitaev in 2005, who, well, it's for, you know, the assumption is, at least at this level, you have a certain subset of, say, R2, and you take a projection in L2 of that space, and then you can describe by a certain infinite matrix labeled by these points in space, right? So the Pxy, as I wrote here, they correspond to sort of the hopping operators or like the hopping coefficients, how you move from y to x. And then, so what does he say? So, well, you say you divide your space up into three regions. I call them A, B, and C. And then you take little triangles, X, Y, Z, where the vertices lie in, like the X lies in A, the Y lies in B, and the Z lies in C. And then you form this sum here. So you sum over all these triangles. And basically what you sum up is, well, Pxy, Pyz, Pzx. So that's basically how your projection travels counterclockwise in this picture. And then you subtract the clockwise traveling. And then there's a strange looking constant, 12 pi I in front. And this constant is supposed to make you land in Z. So the claim is this always gives an integer. Well, I should specify a little bit what we assume on the projection here. So I think also Kitaev says that, well, it has to be like the Pxy have to be rapidly decreasing as the distance of x and y grows in a uniform way. All right, so that's the idea, how you compute an invariant from projection like this. And this is actually used by people in by physicists who were interested in numerical computations of actual systems. So here they of course have a finite system because it was numerical calculations. And well, so if you just do the naive generalization and compute this invariant for this finite system, you always get 0. So that's an invariant that's only really defined for an infinite system. But it is localized in the following sense, namely, if you only take a certain subset of your finite system and divide that into 3 parts, and then calculate the invariant of that, you get an approximation of the actual invariant. And well, you should take this subsystem as you need to try to make it very big, but you also need to make it stay away from the boundary. And so that's indicated in this picture. That's taken from their paper. So here, so there's this delta, which says how big is your subsystem that you consider. And then there's the size of the whole system. And then they plot this here, they plot the quotient. And you see, if your subsystem is very small, so the quotient is very, the quotient is 0, then you end up with a trivial number. But then as you go bigger, you end up going very near to -1, which is the actual invariant of the infinite system. And then you go back to 0 as your subsystem gets bigger and bigger. So that's how you can actually use this. All right. So our question was how do we generalize this to higher dimensions, and how do we even understand this in a sort of geometric way? So let's think about how to generalize this. I want to rewrite this a little bit. So I can write it as follows using a trace. So here I sort of abuse notation and write A, B, and C. So like it's sort of a twofold abuse of notation. First, I want to write it like A for the indicator function of A, and then I also want to write A for the operator on L2 of X that multiplies by the indicator function. Okay, so sort of the compression to the subspace of L2. And I do the same thing with B and C. And so what you see here is that the sum, as Kitaev wrote it in this paper, can be written as a difference of two traces. Once where you do the clockwise, so you sort of do the order A, B, C, and then you subtract the A, C, B order from it. And of course, now you can use cyclicity of the trace and write this, like expand this even more like into 6 terms. So you get a 4 instead of a 12 here, of course, if you do this. And then what you can notice is that, well, these are all sign permutations of 3 elements, right? So any order of A, B, and C that you could come up appears here, and then it's multiplied by the sign, the permutation that you needed to get this. And so, well, written this way, there's an obvious generalization. So to now n like partitions into n plus 1 elements. So we have a partition A0 up to AN of our space X. And so P is some idempotent on our Hilbert space. And then we want to just take the trace over all sign permutations, where you sandwich the projection between these, projections, like compressions onto these subspaces. Okay, so that's a formula that you can write down. And there are several questions that you can ask. Well, first, when is this well-defined, right? So is this sum of operators even a trace class operator so that I can take the trace? Because the P is certainly not going to be a trace class operator.
Question.
Yes.
Do you mean Sn plus 1 in the sum?
I do. Thanks, Ezra. Yeah. Yes. So is this a trace class operator? So the P will never be trace class because it's always going to be a projection onto an infinite dimensional subspace if this is going to be an interesting result. Then, so what do we do? We need to assume on the partition to make this well-defined. And then the third question is sort of, how do I prove some kind of quantization result? Like, when is this contained in Z, right? Well, I mean, here, of course, I need to, it's not contained in Z, but in 4 pi I times Z. So the general, like in general, for general N, there should be some universal constant so that it's contained in this constant times Z, right? So that would be the question. And this constant probably depends on X. So what is this constant? More questions? Okay.
I have a question.
That is, so,
is there a character valued version of this formula? If you have internal symmetry?
You mean like if I have something like time reversal or something acting on the Hilbert space?
And some kind of symmetry, yeah.
Yeah, we didn't think about this, so I can't say anything about it right now. So let's first think about for which P is this well-defined. And so the biggest algebra you could possibly take, I would say, that makes physically sense is the row algebra, which I want to write in this form. So it is, you take the sub-algebra, I call it script B of X, and it consists of all finite propagation, locally trace class operators acting on the Hilbert space. So finite propagation, I'll say something about it in a minute, and locally trace class means like, if you assume, I sort of want to assume that the space is discrete for simplicity, and then if you can write your operator as a matrix, but you allow possibly infinitely many, so the Hilbert space that you attach to each point may be infinite dimensional, and so these matrix entries that I called PXY earlier they're going to be operators, and you want these to be trace class for all x and y. So that's what locally trace class means.
Excuse me.
Yes.
V is infinite dimensional Hilbert space here.
V, yeah. So V is maybe an infinite dimensional Hilbert space, right?
Yeah. Has to be, right?
Yeah. Well, I guess you don't need to take it. I mean, it's.
Oh, if it's finite dimensional, you get something else. You get this uniform or all.
Yeah. So you get a different row algebra. That's right. A different algebra. That's correct. Yes. It depends on the algebra, but it doesn't. So what I meant to say was it doesn't like. I mean, the question of whether this pairing is defined what its values are, it doesn't depend on what V is. Yeah. But to get actually get the row algebra, you need to take V to be an infinite dimensional separable Hilbert space. That's right. Yes, so finite propagation. So that means that so as I said, so you can write the elements of B of X as these infinite matrices, and finite propagation just means that they're sort of concentrated in the uniform neighborhood of the diagonal. And here's sort of a picture. So I mean, I can only reasonably draw this for X to be if X is Z, or maybe R, and that just means that sort of the support of T is contained in this, in this strip here. So this is the diagonal. So the identity operator would just be here identities at each of these points, and all these other matrix entry zero, and like the finite propagation operator is contained in this sort of uniform tube around the diagonal. So that's what finite propagation means. And that's sort of the assumption that I want to keep for the rest of the talk. So the P will always be finite propagation, which is.
Sorry, you mean TXY is not zero? Is zero?
I'm sorry, what?
Is there a misprint here?
So T can be non-zero in here in this tube, and it's going to be zero outside.
So the typo, it should be greater equal than R.
Yes, that's true. Yeah, it should be greater or equal to R. Thanks.
Thank you.
Sorry. Yes. Okay. All right. So how does this relate to coarse geometry? Well, I think it relates to coarse geometry through this like sort of important observation. I think originally made by Rowe probably, or by Higson also, that actually the isomorphism type of this finite propagation algebra, or of the row algebra also, only depends on, well, the large scale geometry of the space, which I don't really want to say what that is. It's also called the coarse structure. But let me just say very briefly that, a metric space also has information on the small scale structure, right? Because it induces a topology. And the large scale structure or coarse structure sort of forgets about the small scale information. So for example, ZD and RD are coarsely equivalent spaces, and they have isomorphic row algebras. Yeah, but of course, non-isometric is metric spaces. Okay, so are there actual interesting classes to detect, right? That's always this game when you talk about observable algebras. Like if they're too large, if you take all bounded operators, then the K-theory will vanish. If you take them too small, that's probably going to be very complicated and you can't compute it at all. So for the row algebra, it's sort of very nicely calculable because, well, it sort of easy follows from my Torres principle that holds for these algebras, that topological K-theory of the row algebra is isomorphic to Z in even dimensions and zero otherwise. So here I assume that X is a Delaunay set in RD, so uniformly discrete and uniformly dense, which is just to say that it's actually, the inclusion is an isomorphism in of coarse spaces, so it really doesn't matter what I put there. It might be Z, it might be ZD, it might be RD, or more generally, any Delaunay set. It's always Z in even dimensions and zero else, where the dimension depends on the RD where we work in. So there are interesting classes to detect, at least in even dimensions, and that's what I'll focus on. So in odd dimensions, there are degree 1 K-theory classes that are non-trivial, and there are sort of versions of the things that I'm going to tell you for that case, but I'm not going to talk about them today. All right, so we were looking at this formula, and we're thinking about when does this make sense? And so the idea is to interpret this sort of using coarse geometry. And so what we need to assume for the partition is that it's coarsely transverse, which is this condition that is on the slide. So if you take any fattening, so that's what the subscript R is supposed to indicate. AI sub R means the R fattening of my set. So all points that are within distance at most R from AI. So if I take the R fattenings of all AIs and take their intersections, then this should be a bounded set. And this statement should be true for all R. Okay. And well, the idempotent I can allow to be in the unitization of this algebra that I looked at earlier. So finite propagation, locally trace class operators. And then the statement is that this pairing that I called Kitaev pairing is well defined for arbitrary n. And why is this true? So that's this condition. I want this intersection to be bounded. And what is this intersection visually? So these are the sets A, B, C that we looked at before. So that's a two-dimensional example. So this is the R, R fattening of the set A. This is the R fattening of the set. Well, actually, it's on the set C, I think. And this is the R fattening of the set B. And well, the intersection is this little gray part in the middle. And you see that's a bounded set. And you can imagine that this is going to be a bounded set for any R, right? And so now my operators were locally trace class. And that this is a bounded set actually means that if you think about it, like this composition that is written in the pairing is actually going to be zero outside a bounded set. And then because of the local trace classness of these operators, you'll get something that is actually trace class, even for each term individually, right? So that's another question that you could ask. Are these terms trace class individually? And the answer is yes in this case. So that's about well-definedness. So now I can say what the theorem is. So take a coarsely transverse partition and let P be an idempotent in this finite propagation algebra. Then so you can allow an idempotent in the unitization also, which is important because K-theory involves unitization. Then for even n, we have this result, namely that this Kitaev pairing is contained in, well, this strange looking constant that only depends on n times z. So we have this quantization result on this pairing. And well, it's zero if n is odd,
Question.
Yes.
First of all, what is X here exactly?
So X, yes. So X can be any metric space, any proper metric space, let's say.
And what is a partition of X?
It's really just it's a collection of disjoint subsets whose union is X.
The subsets have
doesn't matter what subsets. I mean, I probably want them to be Borel or something if I have a continuous thing, so I can multiply
X, like a lattice. Right?
X can be a lattice, yes. So then it can be arbitrary.
Interesting topology, right?
Yes.
So when you say partition, that means like arbitrary subsets which satisfy this transfer subset.
Yes, exactly. Arbitrary.
Wiggle it infinity in some random way.
Yes, doesn't matter at all. So yes, exactly. I mean, this coarse transversality, I mean, you're worried about wiggling at infinity, but I think wiggling at infinity will probably destroy coarse transversality often, if you think about it. I mean, it depends on, like, if you only do it with two sets individually, then it really doesn't matter, I guess. Like if you think about three sets, but yeah. There's no further conditions, then it should be a partition, and they should be coarsely transverse in this sense that I explained. So the goal is to understand the cohomological content, like what's going on here, how is this related to K-theory, what are these A's, like what does this mean from a homotopy theoretic point of view, maybe. And the idea is that this partition defines something called a coarse cohomology class. So I have to explain what coarse cohomology is. So that's something that's associated to, well, say metric space, but it also only depends on the large scale structure of the space, which you can prove a posteriori. And so a coarse cochain of degree n is a bounded Borel function on n plus 1, like x to the n plus 1, so the x plus 1-fold Cartesian product of x with itself to R. It doesn't have to be continuous or anything. It just needs to be, well, I said bounded Borel so that it works nicely if you have a measure and you want to represent on L2. But if you have a discrete metric space, there's no restriction at all. I mean, it should be locally bounded, but that's all. And then what I want is the support condition, namely that the support of this function is bounded whenever I intersect it with some fattening of the diagonal. So delta is the diagonal, so containing of points x, 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 and so on. So n plus 1 times the same point in x to the n plus 1, with multi-diagonal, maybe I should say. And any fattening of this should have a bounded intersection with the support of such a coarse cochain. So that's the support condition on these cochains. And they assemble into a chain complex using the usual Alexander-Spanier differential that you may know from Alexander-Spanier cohomology. And if you don't, that's the formula. And you can check that this actually, preserves cochains with this support condition. And the cohomology of this cochain complex is it's what's called the coarse cohomology groups. And they were invented by John Rowe, well, in relation to his studies on the index of the Dirac operator on non-compact manifolds. And so here's the example that's relevant for us. So if I have a coarsely transverse partition, then this sort of what I define, like denoted by this wedge product. So you take the external product. So that gives you, so each, again, so I use this notation where AI, I denote the indicator function of AI also by AI, right? So these are all functions on X. And the tensor product means this exterior tensor product. So if I have tensor n plus 1 functions on X, I get a function of X to the n plus 1, right? And then I take their signed sum. So and I claim this defines a coarse cohomology class, and it's basically the same reason as I said before. So if you're in the support, so let's like each summoned individually actually is a coarse cohomology class, right? So each tensor summoned individually. So if I'm in the support of one of these summons, then that means that so say I have a point x0 up to xn that lies in the support. And now and that means that xi of like must be contained in a sigma I, right? And now if I also know that this point lies in an R fattening of the diagonal, then that means that all these points can't be too far apart. And so, well, actually, and then I use this boundedness assumption here to show that this support condition for cochains is satisfied. Yeah, so that's the main example for a coarse cohomology class that we need. And you can also show that actually it's a closed class. That's because the A's form a partition. And you have used, so this uses actually that we use this anti-symmetrization. So it defines a cohomology class. So how do we interpret this Kitaev pairing? How do we interpret it K-theoretically? So one of the problems that we have with this finite propagation algebra is, so maybe I should first point out the subtlety. So this argument why this P is well-defined here, right? That crucially used finite propagation for our Ps. And we can probably make it work. So we can make it work if we assume that like these PXYs are rapidly decaying away from the diagonal, but we can't make it work for a general element in the row algebra. Okay, so general, because like we take an operator norm closure and we have no control on these PXYs. And so this pairing will just not be well defined on the row algebra. And so we have to pass to some subalgebra. And yeah, so here I want to talk about this finite propagation algebra. And the problem with that is that operators of finite propagation do not have a nice topology, right? So they're not they're not holomorphically closed in the row algebra or anything, because if you take a holomorphic function of a finite propagation operator, it's not going to have finite propagation. A polynomial of a finite propagation operator has finite propagation, but an arbitrary like holomorphic function will not have finite propagation. So we can't really take topological K theory, we have to take algebraic K theory. Well, that's how it goes. But the nice thing is in degree 0, that coincides with topological K theory. So if we care about that, it doesn't really matter. It does matter for the proof, though. So maybe I should say at this point, I think I forgot that earlier. So for n equals 2, this quantization result of this Kitaev pairing was sort of, Kitaev already gave a proof in his paper, or a sketch of a proof, and some details were later filled in a paper by Elgaard and Frass. So that's basically results from functional analysis. But so we thought for quite a while about it, but I don't think that any functional analytic techniques will help with the higher dimensional case, really. So at least I don't see at all. So basically for the n equals 2 case, you can, there are some things about results about commutators and Fredholm determinants that you can use, but for the higher case, I just don't know how this would ever work.
So Nicholas,
yes.
But if I understand, so again, so this formula actually does not, it is just some element of the row, element of the row algebra projector there.
Yeah, I don't think there's any reason.
Defined formula.
I think there's no reason why this operator should be trace class. Yeah.
So it's really, this formula, you have this K0 count.
Sorry, yes, I didn't get to this formula yet. So I was starting to explain how to get this. Sorry, yeah. Where's the formula? This formula, right? I was starting to explain how to get this formula from a K theoretic, right? Like I was starting to give a K theoretic explanation of this formula.
But the formula only applies to some restrictions.
This formula is for elements of this algebra script to B of X, yeah, for finite propagation operators. But P is a finite propagation operator.
P of X is a finite propagation.
Yes, P of X is always finite propagation, and that's what this argument was for that I gave, that it's multiplied. Yeah. Okay, so the first step is the Chern character map from algebraic K theory of this script B of X, finite propagation operators, to what's called cyclic homology. So I don't have the time to explain what that is if you don't know what that is, but maybe just know that elements are sort of like, it's also the homology of a chain complex, and elements are represented by tensor product of elements in the algebra. And this is an explicit formula for this Chern character map. And then there's another thing that happens, which is the coarse character map, which sends the cyclic homology of this algebra script B of X, finite propagation operators, to coarse homology. So earlier we discussed coarse cohomology. Now I need to quickly say what coarse homology is. So these are it's also the homology of a chain complex, and the degree n part is locally finite Borel measures, which are supported in some uniform neighborhood of the diagonal. That's one way to realize coarse homology. And so the way this coarse character map is defined, well, so this chi of A0 up to AN will be some measure. And so I need to tell you how it pairs with a function. That's basically the Markov-Kakutani-Riesz theorem, that's the same thing. And well, I'll give it to you on elementary tensors, and then you say, well, these are actually dens in all continuous functions on x to the n plus 1. And so it's given by this formula here. It's a similar trace formula to what we saw in the pairing. And also this coarse character map was also invented by Rowe. Basically, that's part of the machinery and coarse geometry that exists.
So you have a question?
Yes, sure.
Earlier. So you have this examples of coarse cohomology classes built out of regions. But does So do you expand the coarse cohomology? Because here you can contract with any coarse cohomology class. Are we missing something just by thinking of these regions?
Yeah. So the question was, are all coarse cohomology classes of this type that I discussed earlier? The answer is no, because if I take like 1/2 times that, it's not going to be, right? So I think
What is the vectors?
they're
It's a vector space, right? So
no, you can't add them, right? So if I have two partitions, I can't, like, if I add these two classes, they're not the class associated with partition again. So I think, so basically, I think what follows from our theory is that at least in Rn, like all partitions give you up to a sign the same class.
because for example, in this here,
Or
F,
zero.
this F's here,
Yes.
examples, this F's kind of like go, actually not just locally bound, but they're bound, right? In the sorry, not the F's, the A's.
Yeah, sorry, the A's, that's not a good notation. Earlier I used A's for the partitions. Here the A's are operators in script B of X.
Yeah, but
So,
just say that
yeah.
you have some functions, and your functions are built of indicator functions of the sets, and they're just actually bound, even though it's not required to force them multiple. But if you just imagine some thing which grow sort of bounded,
yeah.
maybe they give you some new classes you can also consider.
So coarse cohomology can also completely compute it. So on Rn, because it's also coarse homology theory, and it's isomorphic to R and even dimensions and zero. So in degree n, the coarse cohomology of degree n of Rn is R and zero otherwise.
For Rn, but in general.
Well, in general, lots of things can happen. Yeah, I don't know. So basically, here I just know what to do on specific classes. That's what I'm claiming. Yeah. So, and here's the crucial observation that makes all these techniques useful, is that this generalized Kitaev pairing can be written as, in this way. So there's some constant that comes from the definition of the Chern character. But then, so you apply the Chern character and this coarse character map, and then you can pair this. I mean, this thing here gives you a coarse homology class, and then you can pair it with this coarse cohomology class to obtain a priori complex number, right? So that's sort of the cohomological content, as I would like to say. So summarize in this diagram. So you start with algebraic K theory of B of X, take the Chern character, coarse character map, and pair it with this coarse cohomology class, and that's what this Kitaev pairing is, up to some constant that depends only on n. And this already has some interesting consequences, because, for example, it tells you that the Kitaev pairing only depends on the K theory class of P, right? So in particular, if you have another class, another idempotent that represents the same K theory class, then it will have the same Kitaev pairing with any partition as the original class. This is something that you can also prove by hand, but that's sort of laborious. And, so it directly follows from this explicit formula. Okay, so the way we actually prove this, so it's an index theorem, whose proof I can't really give, or maybe I can comment on it in the end. So what's behind all this? So that was our question. And so here's the sort of one answer. So a partition, as we discussed earlier, defines a map to a simplex, like of your space. So the map is like it's an n simplex, so realized as a subset of Rn plus 1, and the component functions are called lambda I. And here's what lambda I is. So you take the distance function from AI, and you divide by the sum of all distance functions. Okay, plus 1, so you don't divide by 0. So this map has what's called bounded variation at infinity. And so this is also some coarse geometry notion. So there's something called the Higgson corona. And the way this works is you take all functions that have bounded variation of infinity. So these are in particular bounded functions, but then they have a certain, so they vary slowly in a certain sense at infinity. I won't give you the precise definition here for time reasons. But so that is a subalgebra of bounded functions, and it's a commutative subalgebra. And so, by Gale-found duality, it is the algebra of functions on a compact space, and this compact space is some compactification of your metric space M, which was, this infinite space M X that we started with. And that's and so the Higgs corona is basically the boundary of the same thing. So the compactification without the space itself. So this lambda, what I'm saying is that, well, it gives you a map that extends to this Higgs corona, and it extends to a map from the Higgs corona to the boundary of the simplex, which is just a sphere. And then there's another machinery from coarse geometry, which is that you can there's a certain pairing of the row algebra with the K theory, so topological K theory of the Higgs corona, and that pairing is integral. So if you know about K theory and cohomology of C-star algebras, so usually what you have is you have the K theory of a C-star algebra, and you can also take the cohomology of a C-star algebra, and you can pair these two to produce an integer. So that's basically what's called an index pairing. And the problem in the setting is that you usually, like for this theory to work well, you need the algebra to be separable. And the row algebra is not separable. And so you can think of this Higgs corona as sort of an analog of the cohomology of the row algebra, which isn't really defined. Okay. All right, so what I need is just this fact. There is this integral pairing, and then the theorem that we prove is that this following diagram commutes. Namely, so the right down composition is exactly the Kitaev pairing. Okay, maybe I forgot a factor here. And the down right pairings is the following. So first there's the comparison map from the script B of X to the row algebra. So these are finite propagation operator, and this is its closure. And then you can also compare the algebraic K theory to the topological K theory, and this gives you this comparison map here. And then you can do this index pairing. And what do you do the index pairing with? Well, remember the Higgs corona had this, like the partition gave you this map to the sphere from the Higgs corona, and you can just pull back a generator of the K theory of the sphere to the Higgs corona and pair with that. So here we're in even dimensions, so n is even, and so we have an odd dimensional sphere at infinity, and that sphere has k1 equal to z, and so this perfectly works out to produce this integral invariant here. And then there's a mysterious factor of 2 pi I to the minus n half that I can't really comment on, which comes from the proof because somewhere along the way we use Bott periodicity, and that somehow produces this factor. So yeah, this sort of top level discussion, I can't say anything about this. So the result is that this diagram commutes. So in other words, it factors through the integers, right? And that's precisely what we wanted to say, right? So it takes values in this particular subgroup of C, which is some multiple of the integers, and that's what this diagram produces. All right. Other questions so far?
Just one limitation. So
yes,
again, the most obvious generalization of this picture you first for slides is instead of say R2 or R4, take some Rn and have some conical subset, and it's everything will apply to that, right? And then in that case, of course, the homology of that subset is going to be what the pairing depends, because in case of just R2 or R4 is only one homology class after scaling, because the infinite just have a sphere. If you have something more interesting at infinity, they're going to have
yeah, so a conical subset won't be that interesting at infinity because I think the coarse cohomology of that is 0 by Flaskless. So you have to be sort of careful that what you produce isn't trivial. And of course, from a coarse perspective,
some say it was in R3, but you can graph and draw a column over that. So that's
a column, okay.
So that's anyway. The simplest thing would just take a circle.
Yeah.
And then you're going to get a copy of R2 embedded in R3. So we know that that's something like you a single invariant. That's what's good.
Yeah, so I don't know what to say about that now. So maybe we can talk after, because yeah.
That's might be something new, not just
Oh, I see. Yeah. Okay.
Single integer which you get in the usual theory.
Right.
R2.
Okay, so you just pointed out that basically if X is just RD or ZD or something like that, there's only one interesting K-theory class up to multiples that we can detect. But yes, so this result indeed that it works for all proper metric spaces and these partitions. So there might be more interesting invariants that we could compute this way. Yes. So let me just in the remaining time quickly talk about something else. So there's something called higher vary curvatures, which were defined by Kapustin and Spodyneiko, and so that's basically a family version of this. So let's consider this algebra B of X superscript S. So S is compact smooth manifolds, and I look at all smooth families of finite propagation operators. And then so I have a projection will now actually be a family of projections parametrized by my space S. And then what they do is they define a closed differential form C of P. So which sort of, so if the dimension of, so they also pick some coarse cohomology class, which roughly corresponds to the space dimension. And then they define a closed differential form of 2 dimensions, so 2 degrees higher than the space dimension, so degree d plus 2. And in such a way that, you know, if the space dimension is 0, it reproduces the Berry curvature that we saw earlier. And so here's very sketchy how this sort of relates to what I told you. So in this case, we start from the algebraic K-theory in Bx of this algebra Bx sub S. So again, like a projection of like a family of projections is just a projection in this parametrized algebra. And then we take a Chern character. Here it's better to go to periodic cyclic homology for technical reasons. And then this sort of maps to this direct sum where you know sort of disintegrate the space and the parameter space. And then on this first component here, so the periodic homology of this the script B of X, you can use the character map and go to coarse cohomology of that space. Well, I extracted the degree n component, and then pair with this coarse cohomology class. And that sort of integrates out this factor. So you land in periodic cyclic homology of C infinity S. And that's well known to be just periodized Durand cohomology of S. So that's the correct recipient of our classes. And this is what I would call the higher Berry curvature maps. So it doesn't only land in like certain dimensions, it actually lands in all even degrees of this Durand cohomology. So there's sort of several more higher Berry curvatures in some sense. And then you can again prove an index theorem like that. So you can compare to the topological K-theory of like some parametrized version of the row algebra, and then take this index pairing, and now you take the Chern character. So the index pairing in this case will land in like topological K-theory of the parameter space, and then you take the Chern character there, which I take in this Durand cohomology class. So that's the theorem that this diagram also commutes. So basically what you get from this is that if you take this higher Berry curvature, then it has an integral pairing with anything that lies in the image of the homological Chern character. So the map from K homology of S to this Durand homology class. So in particular over spheres, and that's sort of the integral that Kapustin, so the theorem that Kapustin and Spodyneiko proved in, I think, for certain spheres. So that's sort of a family version. So one thing that I do not know is that the above map, so that the higher Berry curvature that I defined this way in this abstract way really reproduces the explicit formulas of Kapustin and Spodyneiko. So that's something that is a bit hard to check from this abstract with this abstract machinery. Okay, so one other remark is that you can also look at higher Kubo formula. So there's something called the Kubo formula, which is related to the quantum Hall effect. So it's basically this formula that I wrote down here for n equals 2. And here the x1 up to xn are not a partition of space, but it's a collection of subspaces. Basically for R2, you would pick everything to the right of the x-axis, say, and x2 would be everything to the, like on top of the to the x1 would be everything to the right of the y-axis, and x2 would be everything over the x-axis. And then you take commutators with these indicator functions here. And that's another sort of quantized thing. And we also proved this. And actually, for the proof, this is better because you can use sort of a dimensional reduction technique. So actually, the way we prove this is we prove this inductively on the dimension using these higher Kubo formulas, and then we relate those pairings to those higher Kubo formulas. So another thing that's probably interesting in particular for application in physics, so there's like everything I said so far was about finite propagation operators, but you can also have a version for projections with rapidly decaying kernels instead of finite propagation operators. So not necessarily finite propagation, but the finite propagation decreases quickly. But that is a little bit more difficult because, because one needs growth conditions both on X and the partition. So there's like, it sort of leaves the world of coarse geometry a bit and goes into something where you have to assume polynomial growth conditions. So it doesn't give that clean of an answer somehow. And then there's a final remark that I think I made somewhere along the way already, that there's also a version of this story for odd n, where instead of projections, you take unitaries, and you take something like, so instead of the p's, you put here a u, and then a u inverse, and then again a u, and so on and so forth. And that's related to a pairing on K1. So I think I'm done here. So thank you for the attention.